Okay, while we're getting ready to start, let me just check. Has Yogev Becher showed up? Yogev, are you there? Ron Motzkin?
Yes, I'm here.
Came late today, huh? All right. Okay, so the only one I'm missing now is Yogev Becher. Okay, so let's continue. Hopefully everybody is here. Let's keep going here. All right. So just to go back and sort of review, wheel climb. In fact, let me just show you wheel climb for a moment. So everybody remembers L over V, right? And if you remember, I also said in the European world, you'll sometimes see the term Y over Q. So for example, in that British report that I showed you of that derailment, they actually used Y over Q instead of L over V. You'll use those interchangeably. That's the ratio of lateral vertical loads. Okay. So when we talk about wheel climb, so that's normal wheel rail contact. When we have flanging, this is wheel climb. I love this picture. I don't know. I got a friend of mine from one of the railroad research centers sent it to me. I'm not quite sure how they managed to get this picture. I assume it was a remote video camera, and they were running some derailment tests, and they just caught this climb moment. But you notice the big gap between the flange of the wheel and the tread of the rail. This is what's supposed to be. And this is wheel climb. You see how the flange is hard up against the gauge face of the rail? So the wheel flange, it's climbing up. And this is, again, high coefficient of friction, high L over V ratio, low L over V threshold, and it just picks this up. So this is your wheel climb type of behavior. And with wheel climb, you tend to see these kinds of marks. So you have your wheel flange. Oops. You have your wheels running along here. All of a sudden it climbs like that. And then it has one or two things can happen. You can run along the top of the railhead for a while, or you can just go to the other side and fall down off the field time. So this is fairly typical of wheel climb, though. We have this very short type of mark across the top of the railhead. And this is associated very much with high L over V ratios. Wheel lift, which we just talked about a few moments ago. So yes, those previous ones, sorry. Wheel lift occurs when I have no flange contact, but I have an unloading of the vertical force. So my vehicle is rocking, and my vertical force unloads, and it actually rocks off the top of the rail. Then I come into a curve, and they say that, let's say the rail suddenly moves off to the right, the wheel comes back down, there's no rail, and I have a derailment. So this is wheel lift, usually associated with high lateral forces. Rail rollover. Rail rollover occurs when my L over V forces are high enough to cause my rail to rotate significantly and either go completely on the ground, or this wheel suddenly starts running on the web of the rail and knocks the rail down. So that's rail rollover. And dynamic wide gauge is when I either translate the rail laterally, widening the gauge, and there's usually some amount of tolerance between the base of the rail and the shoulders of the sleeper, or I rotate the rail. I don't rotate the rail enough to roll over, but I rotate the rail sufficiently to widen the gauge. So I have gauge widening, and again, I have the risk of this wheel dropping in right over here. And my L over V forces, of course, are very much dependent on my wheel rail contact forces, as are my stresses, which we talked about in a different case. So, as I indicated, these short tops and marks in the rail are typical of wheel climb, and it has other mechanisms which we'll talk about in a moment. But let me sort of take you to the movies. Let's see if I can do this properly. First thing I want to do is I want to turn on the sound. Okay, share screen. Pull this up. Can you all hear the sound on this movie? Somebody answer. Can you hear the sound?
Yes.
Inspection that is not under load can provide a lot of information about the relative condition of the track structure. However, measurement of track conditions under load is done by a track geometry car and takes into consideration the many forces that affect the track
Now, you
structure
can see by
as
the
a train
computer
moves
system
over.
that this is an old movie. But
Regardless of how
I'm
deviations
not so
are
much
measured,
interested about the geometry
any
car
amount of
here
rail
as
movement
I
that
am
occurs
dynamics.
under load must be added to any measurement taken on unloaded track. There are numerous factors that affect the forces that occur between the train and the track. They include train speed and handling, vehicle
That's
condition,
truck hunting. We'll come back to that.
type, weight, and distribution of load, marshalling of different types and weights of cars within each consist, vehicle motion, track design, and deviations in track geometry. How these forces distort track geometry, or even derail a train, is best understood at the wheel-rail interface. The wheel-rail interface sees a combination of lateral or sideward forces and vertical or downward forces. The proportion of lateral to vertical force determines the angle at which the resultant force will act and is called the L over V ratio. The importance of the L over V ratio is that although lateral forces try to tip the rail over, the appropriate amount of vertical force holds it in place. However, if the L over V ratio increases beyond certain limits, the resulting force can tip the rail and damage the rail fastening system. On the high rail, the increased lateral loading increases wheel flange contact, which encourages wheel climb and rail rollover. On the low rail, if the L over V ratio increases beyond a certain limit, and especially if the load bears on the outside portion of the railhead, as happens when wide gauge exists, the low rail will tip, permitting the wheel to drop. The three common situations that result in an increase in the L over V ratio are lateral force increases while the vertical force stays constant. The lateral force increases and the vertical force decreases, or the lateral force remains constant while the vertical force decreases.
Okay, so that was the first one. Let's see. Oh, I'm going to be able to do this here. Okay, where's this video?
Lateral forces vary according to the following factors: flanging force, centrifugal force, frictional curving forces, coupler forces, buff and draft forces, vehicle dynamics, and track geometry. On a curve, when wheel flanges contact the high rail, a flanging force results. As train speed, weight, and track curvature increase, so does the lateral force on the outer or high rail of curves. Centrifugal force causes the resultant load of the vehicle to shift toward the high rail, and additional lateral force to be applied to the rail. To counteract the additional lateral loading of centrifugal force, superelevation is designed into each curve. The incline shifts the resultant load of the vehicle back toward the low rail. Design speed repositions the resultant load to within a specific distance of track center line. Therefore, the superelevation of each curve is designed to counteract the centrifugal force produced by a vehicle traveling within a certain speed range through a curve with a specific degree of curvature. If the design speed for a curve is exceeded, the risk of spread gauge and high rail rollover increases. Similarly, if train speed is too far below the design speed, the centrifugal force will be insufficient to keep the position of the resultant load from shifting toward the inside rail. Superelevation will transfer excessive weight to the low rail, accelerating rail wear and promoting low rail rollover. However, the largest single source of lateral loading at the wheel-rail interface is frictional curving forces. To steer around a curve, the inside wheel must travel a shorter distance than the outside wheel. Therefore, with two wheels of the same size, the inside wheel would have to rotate slower, or the outside wheel would have to rotate faster in order to travel through the curve as a wheel set. But since both wheels are joined by a solid axle, one or the other would constantly slip because of the difference in rolling radius. On curves up to 2 degrees, and depending on the rail and wheel wear, the conical shape of the wheel tread causes the wheel sets to move toward the high rail. This shifts the contact area of the low wheel to a slightly smaller diameter. Therefore, with each turn, the low wheel travels less distance than the high wheel, allowing the wheel set to steer through the curve without slipping. Unfortunately, wheel wear and rail head profile are never perfect. And on curves over 2 degrees, the wheel set cannot shift over far enough to compensate. The resulting slipping action produces frictional force between the wheel and rail on either side of the wheel set. These frictional curving forces increase the truck assembly's tendency to steer towards the outside of the curve. This steering action forces the rails apart, promoting rail corrugation, wide gauge, wheel climb, and rail rollover. Frictional curving forces can be reduced by appropriate rail lubrication. However, lubricating only the high rail increases the total gauge spreading forces, because all steering forces for the truck must be generated by frictional curving forces off the low rail. On high-degree curves, excessive frictional curving forces can be reduced by lubricating the low rail as well. Rail cars are of different lengths and have drawbars of different lengths that create lateral coupling forces on curves. This results in high opposing lateral forces being transferred to the truck assemblies, which can force the rail out of line or even derail a car. Another similar lateral force is produced by buff and draft, which are measures of the in-train forces that pull and push on the individual vehicles in a consist as the slack in a train runs in or out due to changes in speed or grade. Buff forces in a curve push the truck assemblies of coupled cars outward. The additional lateral force increases the probability of out-of-line and wide gauge, or possibly low rail wheel drop, and the resulting high rail rollover. Draft forces in a curve pull the trucks of adjoining cars inward, encouraging high rail wheel lift, or gauge spreading and high rail wheel drop, resulting in low rail rollover. The principal dynamic vehicle action that contributes to lateral forces in tangent track is truck hunting. High speeds and short, light, or empty cars on tangent track can contribute to truck hunting. But the problem is primarily a result of truck design, bearing type, worn wheel tread, and excessive flange clearance. As wheel sets deflect back and forth, they apply intermittent lateral loads on one rail, then the other. Track geometry can produce lateral forces as well, primarily through changes in alignment. When a vehicle enters a spiral, the trucks must be turned to follow the track. The forces to turn the trucks are generated by the lateral forces between the wheels and the rail. Track geometry defects can also induce lateral forces, primarily through poor alignment or variation in gauge. For example, because of the increased flange clearance, wide gauge will increase the forces generated by truck hunting at higher speeds. Tight gauge reduces forces created by truck hunting, but causes hunting at lower speeds. Vertical forces are an integral part of the L/V ratio. Even if the lateral force remains constant, an increase or decrease in vertical force has a major effect on the resultant force. Vertical forces vary according to the following factors: vehicle weight, unbalanced elevation in curves, vehicle dynamics, track geometry, and coupler forces. Vehicle weight produces the most significant vertical wheel load, simply a measure of the static weight of each car and its contents, divided among the various wheels. However, when a rail car rolls along the track, rocking, bouncing, and other dynamic actions or reactions change the value and position of the vertical force of each wheel on the rail head. Balanced elevation in a curve occurs when the amount of superelevation present positions the resulting total load from the vehicle on the center line of the track. But if the train exceeds the speed for which the superelevation is designed, the elevation is unbalanced. The resulting total load on track is shifted to the high rail. Likewise, if train speed is too slow, the resulting total load on track will be shifted to the low rail. Either situation will cause premature wear of the rail and possible spread gauge or misalignment. Vehicle dynamics contribute primarily to varying vertical force at the wheel-rail interface. The suspension of rail cars permit the car bodies to bounce up and down, pitch, and to roll from side to side. When a car bounces, the vertical loading on both truck assemblies increases and decreases simultaneously. Pitch occurs when one end of a vehicle goes down and the other end goes up. The result is a varying transfer of vertical force between the truck assemblies, resulting in repeated high vertical loads. And when a car rolls from side to side, the vertical force alternates between the rails, resulting in wheel unloading and wheel lift. Defects in track geometry, such as poor surface or cross level, excessive warp, twist, or runoff, and discontinuities in the running surface, such as bad joints, points, or frogs, also affect vehicle movement. These conditions vary the vertical force and therefore the L/V ratio at the wheel-rail interface. Poor surface can promote bounce and pitch because of the change in uniform level profile. Mismatched, bent, or battered joints and worn points and frogs at switches and railway crossings can contribute to pitch and roll movements as well. Poor cross level can initiate roll. But the most dangerous form of roll is harmonic or resonant roll, known as rock and roll. Rock and roll occurs when a car with a high center of gravity, traveling on soft track at certain speeds, moves over a successive series of low spots or joints with spacing similar to the distance between the center of the trucks. This rocking magnifies the alternating vertical load on each rail, causing wheel unloading and possibly wheel lift. If this occurs on a curve, the wheel may come back down with the flange on top or to the outside of the rail. On long rail cars, excessive warp and twist in spirals and on the curves can force the suspension of diagonally opposing truck assemblies to their limit. The differential load results in diagonal unloading and possible wheel lift on opposite corners of the car. The problem is further compounded by the transfer of much of the load onto the diagonal side bearings, which prevents the trucks from turning to follow the spiral or curve. Therefore, under excessive warp or twist when leaving a curve, the leading truck assembly is most likely to derail. When two cars move over excessive runoff at the end of a track lift or raise, the rapid change in uniform surface profile over a short distance causes pitch and bounce at high speeds and can actually uncouple cars at low speeds. The vehicle dynamics of coupled rail cars moving over track surface irregularities produce vertical coupler forces. When couplers bind under buff or draft, some of the vertical forces of bounce and pitch, normally absorbed by the suspension of one car, can be transferred to the other, intermittently increasing the load on one truck assembly while unloading the other. We have also seen how poor surface, such as mismatched, bent, or battered joints, and worn points and frogs, can contribute to bounce and pitch and the resulting vertical coupler forces.
Okay, let's see if we can find the last one.
The wheel rail profile can also determine whether an L over V ratio is acceptable, since the wheel rail contact point determines the position of the resultant of lateral and vertical forces. With a new wheel on new rail on tangent track, the point of contact positions the point of loading over the center line of the rail, and flange contact is induced only by lateral forces, except in curves over 2 degrees, where flange contact is normal. However, with a new wheel on a worn rail on curves, one of the points of contact of the vertical load is on the gauge side, making it easier for the wheel to climb the high rail. In turnouts, excessive play in spring frogs or an insufficient height difference between the point rail and stock rail will cause problems with worn wheels. With a trailing movement through a turnout, the false flange of the wheel may cause spring wing rails or the stock rail to overturn. On tangents, if the head of the rail is allowed to become excessively flat, the vertical load from worn wheels will shift back and forth between the two possible points of contact, inducing truck hunting and excessive wear on the gauge side of the rail. When considering vertical forces, remember that any time the load of one wheel decreases, its share of the axle load may be transferred to the opposite wheel of the set, to the other wheel set, or to the other truck assembly. If the increased vertical load is not properly centered on the rail head, low rail wear increases, as does the probability of the low rail tipping, allowing the wheel to drop inside the low rail. It is important to understand the forces at the rail-wheel interface as the result of the interaction between track geometry, vehicle dynamics, and the wheel-rail profile. This way, the effect of specific track conditions on trains can be better understood when planning and performing track maintenance.
Okay. So let's check for a minute. screen. This is where we were. Yes. Okay. The move, I always try to figure out where's the best place to put the movies. I move them from the end of the class to the beginning of the class because there's a huge amount of information. But what I really like about the movies is the visualization, the pictures of the vehicle rocking, the pictures of the truck hunting, the pictures of the vehicle curving, and some of the graphics are very clear. Before I keep going, because I'm going to address some of these things further, anybody have any questions that sort of popped in your mind in the movies? By the way, you noticed everything was in the using North American terminology. This movie was produced by Canadian National Railroad actually produced these movies. But anybody have any questions that came up that popped up when they saw the movies? It's a bit overwhelming. I'm not trying to put anybody on the spot. Okay, so let's go over some of the things that we talked about in the movie in a little bit more detail. So it gives me a chance to discuss them a little bit much. So the first concept was harmonic roll or rock and roll. So let's get my. There we go. Oh. Okay. So harmonic roll or rock and roll, which is that side-to-side rocking of the car. Now, it most likely occurs on jointed track, but it does occur on welded track where you have a series of battered joints. Again, this is the case, though, with the joint with battered welds. So this is the case where either the joints or the welds are staggered, which is a common design in the heavy axle load world in particular. So when the bogie, so typically or traditionally, these joints are roughly around 12 meters apart. And so if your bogie spacing is around 12 meters, which is also a fairly common type of bogie spacing, then you can generate this resonance phenomena. And the resonance phenomenon, as I mentioned before, occurs in this critical speed range, about 25 to 40 kilometers per hour. So we've many times seen the situation where a vehicle going at 50 kilometers per hour is no problem. A vehicle going at 15 kilometers per hour is no problem. But the vehicle going through the track at 35 kilometers per hour resonates. And we've seen that. I've seen derailments where the track speed was above the critical speed range and nothing happens until a maintenance officer saw the defects and said, well, I better put a slow order on the track, and he slows the trains down to 30 kilometers per hour, and all of a sudden they derail. So again, harmonic roll, and I think the illustration in the movie was even more clearer, so you can see how you generate this side-to-side movement around the longitudinal axis of the track. And this is the type of track that can definitely initiate harmonic roll. Now you're going to say, my track doesn't look like that, but take a look at some of your sidings and some of your yards and some of your lesser known track. And I bet you have track that looks like this too. Pitch and bounce, and again, the movie showed a pretty good example of that. Pitch and bounce happens when I have square joints, which is more common in the UIC world. So I have square joints, My joints or my welds are opposite each other. And so now I have a picture. So I have to draw you a picture. So now I have my vehicle pitching and bouncing, fore and aft motion. So the front goes up, the bottom goes down, the front goes down, the bottom goes up. This is also a dynamic behavior that can result in wheel climb and bounce. This also happens at a little bit higher speed. So we see this at around 70 kilometers per hour. We also see this where there are transitions in vertical stiffness. So our friend, the track modules. If you have a massive, significant change in track modules, where do you see this? Bridge abutments is one of the biggest ones, where all of a sudden you go from soil to a concrete pier, and your track runs over it, but the stiffness has changed. Road crossings are common stiffness transitions. Transitions from wood to concrete sleepers see this. Sometimes even going into a turnout can see it. And it's also related to the truck suspension. A softer suspension is more prone to good pitch and bounce. Now, truck hunting, and again, you saw some really, really nice videos of hunting. Hunting is my lateral oscillation of my axle set. Which is going from side to side now as it goes down the track. Now, hunting is associated with higher speeds. And in fact, most vehicles, particularly vehicles that are designed to operate at higher speeds, like intermodal vehicles or passenger vehicles, truck hunting becomes a design criteria. And you design the vehicle to try to bring the hunting speed above the operating speed that you're looking at. Typically, for freight wagons, empty or lightly loaded cars are the ones that are most subject to truck hunting. And there you see truck hunting. This says speeds above 75 kilometers per hour. But it's a little bit more common speeds in the 100 to 120 kilometer per hour range and above, which tends to be the passenger speed range. So again, in designing passenger speed equipment, hunting speed is actually a fairly standard criteria. Now, as mentioned in the movie, hunting occurs on straight track. So this is a place where this is where we generate very high lateral forces on tangent track. This is one of the most significant lateral force environments on tangent track. And we see it in good quality track. If the track is very poor quality, it doesn't allow the resonance phenomenon of the truck hunting to occur. It disrupts the resonance. So this is really good quality mainline track. Sometimes you see it with worn wheels, but not worn wheels past the standard, just worn wheels that are already seeing some hollow in the tread of the wheels. So what tends to accentuate this type of behavior is if the wheel tread wears in a pattern like that, which we call a hollow worn wheel, which by the way is a fairly standard wheel wear pattern for wheels, since you're supposed to be riding in the center of the wheel. So that's where you're going to get most of your wear. So truck hunting, again, is this lateral force back and forth between the wheel. Sometimes you have an angular effect in there. Sometimes it just stays constant. So track train dynamic responses are becoming more and more critical in defining how we look at the excitation of the track to the vehicle. And so the newest generation standards for track geometry have started to include dynamic response characteristics. In fact, there's a new class of measuring equipment called vertical track interaction equipment. So For example, in the United States, we put these VTI or vertical track interaction packages on locomotives, and it measures the dynamic of vertical, lateral, and longitudinal accelerations. And recent sets of standards have even introduced dynamic response standards to augment the traditional track geometry standards, which we'll talk about a little bit later today. But the type of standards that you can see when these are usually associated with high-speed track. So, like in the United States, for example, the track for speeds of around 200 kilometers per hour or higher, the standards now include dynamic response characteristics. For example, Amtrak in the Northeast Corridor, which operates 200 kilometers per hour plus, they're required to take dynamic response measurements every 30 days. And that includes car body lateral acceleration, car body vertical acceleration, and truck lateral acceleration. So car body lateral acceleration is measured on the floor of the car body, but truck accelerations are measured down in the bogie, where you're below the secondary suspension, but above the primary suspension of the vehicle. So typically, standards that we can see include car body lateral accelerations are required to be less than a half G peak to peak. Car body vertical accelerations have to be less than 0.6 G peak to peak, where G is the acceleration of gravity, 9.8 meters per second. Somebody asked me if you need to carry it out to 5 decimal places. No, 9.8 or 9.81 meters per second works fine. Truck or bogie lateral accelerations, the current standards include have to be less than 0.4 G RMS, which is root mean squared. So no longer peak to peak, but a mean removed RMS. So you have to look at root mean square, basically squares the peaks, takes the square root of the squares of the peaks after you remove the mean. So you take, if your signature looks like this, your mean is this. You have to mathematically remove the mean, calculate your RMS, and then it has to be less than 0.4 G. Curving forces we've talked about before. You both have parallel and radial bogies. So a lot of passenger vehicles make use of radial bogies, radial trucks, where the axles align, change their rotation to align with the radius of the curve, the instantaneous radius of the curve. That gives you that reduces your curving forces. But a lot of vehicles, and almost every freight vehicle for sure, has what we call parallel bogies or parallel axle trucks, where the axles remain parallel, so they do not align radially with the truck. This is a cheaper design, which is why it's used very often. And you see it, as I say, primarily in freight vehicles, and these generate much larger curving forces. We already talked about wheel conicity and the difference in conicity and the issue of steady state and dynamic forces, so I'm not going to go over those again. They're all experts in that. Okay, we also talked about super elevation and cant, so in the interest of time, I'm going to zip through that again. I'm not going to repeat that. Again, supervelation and cant are just the same words in two different worlds. It is the design difference as opposed to cross level, which is the non-design difference. So if I have one rail higher than the other rail, if I'm on a curve and I'm supposed to have 150 millimeters of cant, and I have 150 millimeters of cant, then I have 0 cross level, because that's what it's supposed to be. On the other hand, if I go out there and I measure 200 millimeter height difference between the high top of the rail and between the high rail and the low rail, the top of the high rail and the top of the low rail, then I have a 50 millimeter cross level or variation, which is a defect. And of course, it's designed to compensate for centrifugal force effects, which we've already discussed. So I'm going to skip through a lot of those. Okay, so we've already gone through these equations. I'm going to skip through this in the interest of time. We talked about unbalanced or cant deficiency, which is the amount of overspeed permitted on the curve. And the equation, if you recall, was this. We all did this. I don't think anybody had any problems when we did this in the assignment. I didn't see any issues, so we're going to go through that. If I have excessive elevation beyond what I require, and that becomes an issue when we have mixed traffic. So if you have passenger and freight on the same track, if you elevate the track for the passenger, so let's say passenger is the dominant traffic on a piece of track, and I elevate the track for passenger, then my freight, my lower speed freight, are going to generate higher forces to the low rail, which is going to cause increased track damage to include low rail crushing, tie damage, track geometry degradation, etc. And we've gone through that. I'm going to skip through a couple of these because we've already had this. We talked about the Nadal equation, so I'm not going to repeat the Nadal equation. And I think everybody, does anybody need me to go over the Nadal equation, or are you all up to speed with that? Everybody's silent. I guess it's already dragging along. Or either that, I put everybody to sleep with the movies and nobody woke up. Okay, so you remember the Nadal equation gives you the L over V threshold for wheel climb. In other words, the value, the L over V level above which you get wheel climb. And it's a function of the coefficient of friction between the wheel and the rail. So truing the wheel changes the coefficient of friction, lubricating the wheel, lubricating the rail, grinding the wheel, all changes. So truing the wheel and grinding the rail increases my coefficient of friction, makes it higher. Lubricating my wheel or lubricating my rail reduces my coefficient of friction. And then the Nadal equation includes the wheel flange angle, which is the angle at the wheel flange. And as you recall, again, we showed this. So as for a given wheel flange angle, as the coefficient of friction increases, the L over V threshold decreases, which means the risk of wheel climb increases. So if I have a coefficient of 0.3 and a flange angle of 68, Nadal tells me my L over V threshold is about 1.25. If I had very rough rail, so I had a coefficient of friction around 0.6, my L over V threshold is 0.7, much lower, which means it takes much lower lateral force or a lower unloading of the vertical force to get me to that threshold and cause wheel climb. So again, sensitive to coefficient of friction. And that's what we saw in the WMATA derailment and the British derailment both, where you had truing of the wheel caused a high coefficient of friction. So all of a sudden, we were at the low threshold, very high risk of wheel climb. Now, one of the weaknesses of the Nadal equation is the Nadal equation is only sensitive to wheel flange angle. So what happens to my rail? When my rail wears, I can also get a flange angle on the rail, which is in this particular case defined as my angle phi, as defined here. So it turns out that the gauge face wear angle can be a factor in wheel climb, just like the wheel flange angle is. But the mathematics are a little different because the Nadal equation only deals with the wheel, with the gauge, with the wheel flange angle. So if I go through the analysis, an equivalent analysis to the Nadal equation, except in this case, I look at the gauge face angle, I get an equation that looks like this, where my L over V threshold, this is just like the Nadal equation, this is the L over V threshold, is equal to the tangent of beta minus mu prime, where beta is 90 minus phi. So in fact, beta is that angle here. And mu prime is the arctan of the coefficient of friction. Now, this is where you got to be really careful to make sure if you're using a spreadsheet, you got to make sure you stay in radians and not in degrees, because otherwise you're going to be in trouble. But those of you, I'm making the assumption that everybody understands what an arctan is. I mean, this is enough of a level where I don't need to go explain what an arctan is. If not, Google it. Most of your hand calculators do not only the sine, cosine, tangent, but arc sine, arc cosine, and arctan. So the L over V threshold is a function just like the Nadal equation. It's a function of the coefficient of friction and the gauge face wear angle, which we define here as phi. Why do we define phi rather than the beta? Because you can measure phi. You can't measure beta, unless you just calculate beta as 90 minus phi. I can measure beta. A typical laser profile measurement system will easily produce a phi for you, or you can actually go out with a hand gauge and measure phi. So just to give you an example of how it works, if my rear gauge face angle is 30 degrees, my coefficient of friction is 0.5. My L over V threshold is tangent to beta minus mu. So beta is 90 minus 30. Mu prime, this should actually be mu prime, is the arc tangent of 0.5, which is 0.43365, and my L over V threshold in this particular case is 0.66, which tells me that 30 degrees is a pretty high number. Now, we know coefficient of friction of 0.5 is pretty rough, but 30 degrees is also a fairly significant amount of gauge face wear. And so I know railroads that have standards set their gauge face wear angle between 28 and 30 degrees to remove the rail. And again, if you do a sensitivity analysis, if you fix your gauge face angle, let's say we fix our gauge face angle at 30. So as my coefficient of friction increases, so my L over V threshold decreases. As my coefficient of friction decreases, my L over V threshold increases. Exactly the same as the Nadal equation, except with this particular relationship. So again, wheel climb is sensitive to both rail gauge face angle and to wheel flange angle. Same way. If I have too much of a gauge face wear angle, I have my L over V threshold decreases, my risk of climb increases. If I have too high a coefficient of friction, my L over V threshold decreases, my risk of climb increases. And as I said, I've seen railways set, like for example, I believe the British use about a 30-degree flange angle as a wear limit for their standards, if memory serves me right. And I'm going to skip this discussion of the DeBart derailment, other than to tell you that this was a case where we found a gauge face, significant gauge face wear angle, and it caused the derailment. Now, I mentioned that there were other criteria for wheel climb, the Weinstock criteria, which is less conservative, the effective time duration, which we also talked about earlier. I'm going to skip those. I mentioned in addition to, now the Nadal limit or the gauge face wear angle limit I gave you is a single wheel L over V threshold, but there are standards out there that look at both single wheel L over V on the same axle. So a net axle L over V. Okay, so let's do this one. Okay, so this is my outside rail. This is my inside rail. Inside, outside. This is the wheel. This is the rail. Okay, the Nadal equation is a single L over V on the outside. Net axle would look at combined vertical and combined lateral, so it will be L1 plus L2 over V1 plus V2. That's in addition to. So what we see is we see standards both for single wheel L over V and for truck L over V or an axle L over V. And also we'll also see it for a bogie or truck L over V, where it's L1 plus L2 plus L3 plus L4 divided by V1 plus V1 plus V2 plus V3 plus V4. Okay, I'm going to skip some of these. Very quickly, there are commercial systems out there that can both measure L and V and L over V ratio. They all work off of strain gauge principles. This is a typical lateral lay where you put a chevron, you put your chevron gauge, you put your gauges and a chevron array on the base of the rail. Oops. Tell you I can't draw well here. So these gauges here are your 4 strain gauges. They go on the base of the rail. And then they're hooked up, and you're actually what you do is you're calculating lateral shear here, lateral shear here, and you're subtracting it to get the lateral force in between here. Verticals work very similarly, except they put the strain gauges on the web of the rail. Again, here's the strain gauges, and you can hook it up again, the exact same principle. Vertical shear here, vertical shear here, and the difference is the force. And you can you can hire people for this type of instrumentation right now. There's an example of vertical force measurement from the vehicle. Now, I just love to ask this question. Yes or no? Is this a vehicle? These 4 wheel impacts. Is that one vehicle? Yes or no? Anybody want to answer? No. Because if you remember correctly, I have a bogie here, then I may have another 10 or 12 meters between the other bogie. On the other hand, I have another vehicle over here that has a bogie over here that's much closer. So in fact, My vehicle would be that and that. And these are typical measurements that we see of vertical wheel rail forces.
So, sorry, can't see the color. Can you change color?
Yeah. Okay. So again,
On the yellow graph.
okay. So this is, oops. This is one vehicle. This is one bogie, and this is the other bogie of the same vehicle. This is another vehicle. Bogie, bogie. So what you're looking at here is the end of one vehicle and the start of the second vehicle, because the distance between the bogies at the end of one vehicle and the start of the other vehicle is closer than the distance between bogies in the same vehicle. And you can look at, you can, this is, now remember I talked about all that nice fatigue loading, and we talked about the alpha sub I distributions. This is how we get the distributions of vertical wheel forces, which are then used to calculate stresses. Now, I think I mentioned this before, but it's worth mentioning now. The industry has moved very aggressively towards putting limits on vertical forces. So in addition to having traditional limits for the size of the defect, which has been the traditional ways of doing things. So let's say you have a wheel flat that's limited to 75 millimeters or 100 millimeters, or you have an engine burn that's limited to 12 millimeters. What we have also done, now that we have the ability to measure wheel rail forces in the field, and these are commercial systems that are out there, in North America, there is a 400 kilonewton threshold of dynamic forces above which wheels must be replaced. Amtrak in the Northeast Corridor has a limit of about, right now has a limit of about 266 kilonewtons. If they measure a dynamic force on the Northeast Corridor greater than 266 kilonewtons, they will take action. They will remove that vehicle and replace the wheels or take the vehicle out of service. And what I'm seeing in the UIC world is I'm starting to see standards being looked at where you're looking at if the dynamic load is more than 3 times the static load, then you suddenly are going to have a criteria to remove the vehicle. So, for example, if my force is about 120 kilonewtons, my wheel load is 120 kilonewtons, and if I see 360 kilonewtons, I will take that wheel out. If my force is 100 kilonewtons, and I see 300 kilonewtons, I'll take that wheel out. If my static force is 75 kilonewtons, and I see 220 kilonewtons, I'll take that wheel out. And the wheel load impact detector is one of the commercial systems that are out there that's very, very widely used around the world. And I'm not going to spend a lot of time talking about that. I mentioned there are commercial L/V detectors out there. There are also instrumented wheel sets, which are still more of a research tool than an inspection tool. And I think I'm going to skip that. I'm going to stop here. I want to get into track geometry real briefly for the last hour. So let's take a 15-minute break. Any questions before I leave wheel rail dynamics? I'm not getting a lot of questions, which makes me really nervous.
Can you please upload the videos to the Moodle?
Well, I can upload the videos to Moodle because I'm not really allowed to release the vehicles.
Oh.
I'm allowed to show them. So basically watch them I'm uploading this video on Moodle. So you can watch the videos on this recording.
Right, thank you.
So When I was given the videos, I was told that I really can't distribute them as is, but I'm allowed to use them on my lectures. And since I'm recording my lectures, you'll have to look at it that way.
Okay.
Okay. All right. Let's take a 15-minute break, and we will resume. I guess 7 o'clock your time.
And I have a question.
Yes.
Allan.
Yes.
About the L over V, the
Yes.
ratio. It's a bit, I don't know, it's a bit complicated to understand. What does it mean? If the L over V is high or low, what does it mean?
Okay. So there are two concepts. So what the Nadal limit gives you is the L over V threshold. In other words, the L over V limit.
Mm-hmm.
Okay. So you want the limit to be as high as possible. Because if your limit is low and you have any sort of high forces, you're going to be above the limit. You're going to run the risk of an accident or a wheel climb. So you want your limit or threshold to be high. The actual L over V forces are what you measure. When you go out, you measure your lateral, you measure your vertical, or you model it with the computer modeling, and you get the lateral and vertical forces. Those are whatever you measure. If your L over V ratio is above your threshold, then you have the risk of wheel climb. If you're below the threshold, you're below the risk of wheel climb. So the threshold you want to be as high as possible. The forces you want to be as low as possible. Is that clear?
So the interest is that the V should be higher, the V force.
Okay. If you let me share my screen here. Okay, so okay. This is my L or Y. This is my V or Q. So basically, you're interested in L. Let's see if I can do this. You're interested in L, you're interested in V, and you're interested in L over V. All three separately. So for L, you generally want your L's to be as low as possible because you want to keep your L's low. V is a funny animal. V can't be too high and can't be too low. If V is too high, so if, for example, if it's greater than 400 kilonewtons, for example, or greater than 300 kilonewtons, it's going to break things. You're going to break your rail, you're going to break your wheel, you're going to damage your track, you're going to crack your sleepers. So you can't have V too high. Mm-hmm. You can't have V too low also, because if V is too low, then there's nothing holding your wheel down on your rail. And there's nothing from keeping that wheel from bouncing up and bouncing up too much and then derailing. So that's why with your L over V ratio, you can have a high L over V ratio with either a high L or a low V. So V sort of has to balance in between. Ideally, you want V to be sort of, plus or your static wheel load plus or minus 50%. That would be perfect. Maybe 200, maybe 100% on the vertical side. But you never want your V to go down to less than half of its static load. And most railroads hit your safety standard at around 25%. And then L over V itself, your L over V, you want your L over V's to be low because you want to reduce the risk of climb. But the threshold, the threshold for wheel climb, which is what we're calculating with the Nadal equations, for example, that you want high, because that's your limit. You want your limit, your safety limit to be high, but your actual values to be low.
Okay.
So you really got to look at L separately, V separately, and then L over V together. All three of them have value looking at them independently.
Okay.
All right, let's take a few minute break. I'll see you back here at 7.